Hi, welcome to this video series on linear algebra for business analytics. My name is Teja, and in this video, we're going to look at the notion of inverse of a matrix and how it's related to, for example, linear regression, and also the topic of our last video, which is the determinant. So for that, let's start with this notion of system of equations. System of, let's say, linear equations. So what do I mean by the system of linear equations? System just means a collection for us here. And what are linear equations? So linear equations, let's say I have some unknown quantity, which is x units of something, y units of something, and z units of something else. Then a linear equation is, for example, something like this: 4x plus 2y plus 6z is equal to 2. Okay, this is a linear equation. It's just the addition of these unknown quantities, scaled unknown quantities, and that should be equal to some other quantity that we know, which is, for example, here 2, an equation, because this is an equality here. And similarly, we could have more than one equation. So let's say it's 0x plus 3y plus 2z is equal to 1. Okay, so see that here I put the coefficient as 0. And first of all, these coefficients need not even be just whole numbers. I can have 1.1 times x plus 2 times y plus 10 times z is equal to 0, for example. Okay, so this is a system of equations. I have known that I had 3 unknown quantities, and I have written 3 equations here. This is because if I have more equations, then hopefully those equations are redundant. So for example, if I had one more equation, which is 10x plus 3y plus 4z is equal to 100, okay, you can see that maybe there's some unknowns x, y, and z, which will somehow satisfy these 3 equations. But then the value of x, y, and z that I will find may not satisfy this last equation, for example. So the number of equations, if they're more than the number of unknowns, hopefully the additional equations are redundant in some way. Okay, and we'll kind of revisit this point potentially later. So this system of equations can be actually written in a compact way. So let's collect all the coefficients. For example, in the previous case, let's look at only the first 3 equations. It's going to be 4, 2, and 6, 0, 3, and 2, and 1.1, 2, and 10. So that's, we collected the coefficients, and we have written it as if it's a linear transformation, right? So that's our matrix A. And if you look at the right-hand side, if we collect these what are called residuals, or I guess the right-hand side, 2, 1, and 0, this looks like a vector, right? So the system of equations is in a compact form can be written as A times v vector is equal to, let's call this vector b. It's b. Okay, so this is something that we're familiar with. A is a linear transformation. It's taking an input vector v, and it's going to output a vector b. And what is this v vector? It's nothing but x, y, and z in its first, second, and third coordinates, right? So so the system of equations is nothing but a linear transformation of an unknown vector to a known vector, right? So how do we find so this is what a system of equations is, and let's not worry about how to find this solution computationally, but let's first actually tie it back to this notion of determinant. So determinant of A kind of impacts whether we can find B or not. Okay, and how is that? If determinant of A is not 0, so it's not 0. So not 0, I'm just writing it as equality and cross it over. So sorry, just once. Okay, if determinant of A is not 0, then there is a V. So that's the cool part, that there is a v that you can find that satisfies that this system of equations, or basically there is an input vector which I can find that will give, by the action of a, the linear transformation, will give me this known vector b that I have. Okay. And so if there is a v, so then I can find the v, and symbolically we can think of this as v getting transformed by a to a vector, intermediate vector, that was b, right? And then that vector, um, now we said that given that vector b and the linear transformation, I can also find v, which means that, so this is actually just b, I can apply another matrix, and I'm gonna apply another linear transformation, and I'm gonna represent it in a very unique way. I'm just gonna use this notation a to the power -1. Okay, it's as good as saying I'm gonna apply another transformation which, given the output vector, gives me the input vector. Okay, so if I apply this transformation on b, it gives me the input vector. Okay, so that means that this combined action of this transformation, so this is the transformation A inverse. Okay, so A to the power -1, it's actually just a symbol for a transformation, times, as in times A, which is this, we saw this matrix composition, right? So linear transformation, composition of linear transformations, can apply one linear transformation of the other after the other. So this net effect is going to be that the vector v is unchanged. It's in the same location as itself. Okay, and this thing has a name. It's called the inverse of a. Okay, it's just called the inverse of a because it inverts. It kind of kills all the scaling and shift. It's not shift. But scaling and directionality change that A induced, the linear transformation A induced, it just negates it. So that's why it's called the A inverse of A. Okay, so note that first of all, for us to go back from V to B and back from B to V, the dimensionality of V vector should be the same as the dimensionality of B vector, which means that A is a square matrix. And square matrix just means that the number of rows and the number of columns of a matrix are the same. Okay, so that's what the inverse is. We'll not worry so much about the computation. How is inverse computed, except to say that so let's think of linear regression, right? So I'm just going to motivate linear regression and then try to circle back to saying why we don't really, what is the computational issue that how is A inverse computed, for example. So in linear regression, you have, let's say you have data now. So it's a different type of equation. Here I have the data, which is let's call this data, where each row represents the observation. For example, remember we had age, education, and other feature values for each observation. Maybe we collected 100 of them. Okay, and there is an unknown model. I'm going to call it a model. So this is unknown model is again 100 dimensional, let's say, and we have measurements of how, and we are trying to predict income here, remember. So maybe we have measurements of all the incomes of all these 100 people. Okay, so we have this data matrix, which is a transformation. We have a model, and it predicts the income. So what is the actual so let's say this matrix is beta 1 all the way to beta 100. Then our model is actually that income can be predicted as beta 1 times age plus beta 2 times education plus other things. Okay, so this is what a linear model in linear regression just means. And to solve for the model, you actually just do a matrix. You just multiply with the data matrix times this model vector is equal to something that you know. These are the income levels, incomes. Okay, just stacked one on top of each other. So computing beta vector, which is the model, is the same as trying to find the inverse of the data matrix. If you can find, so I mean, it's not the same, but to compute the beta vector, you can apply another transformation, which is the data inverse matrix on both sides, right? Data inverse. And we know that this net effect is to bring beta to itself. So data inverse acts on the income vector to give us the beta vector itself. Okay. So this is just an interpretation of why inverse and determinants and system of equations are related to linear regression. Now, so let's think of, but we should ideally, so although I've talked about the inverse, ideally nobody actually computes the inverse in practice, actually. So nobody computes A inverse. So whenever you have a problem which has, whenever you are thinking about inverses, only think about solving a system of equations. Of course, these two problems are not the same. So whenever you come across a step in your, maybe you're doing some machine learning modeling and you involve a step where, maybe you are thinking you want to compute an inverse. Instead of doing that, maybe all you care about is not the inverse itself, but maybe you just care about some corresponding vectors. And if you want to solve for those vectors, maybe you should just solve a system of equation, because solving a system of equation, it turns out, is easier in terms of computation than to find the inverse. But this is just an aside. So let's get back to this notion of this notion of system of equation. So let's say, so we said when determinant is of A is not 0, then something happens. What if determinant of A is 0? Okay. So remember from the last video, when determinant of A is 0, that means that we have squished the input space, right? Remember, we said if we go from, if A is a transformation which goes from 3 dimensions to 2 dimensions, or goes to 1 dimension, right? Which means here it's a plane and here it's a line. Okay, that means that many vectors all get transformed to the same vector. Okay, this is what, so if A is a transformation which goes from 3-dimensional space to 2-dimensional space, maybe the two vectors, for example, 10, 2, and 5, and another vector maybe 5, 3, and -1.1, let's say, both map to maybe a vector like 3 and 2. Okay, so both map like this. So if A is a transformation which does that, then we know that A times V is equal to B. This will have, this B vector will be in 2 dimensions and V vector is in 3 dimensions. Then it's not possible for you to find a single V given A and B, right? So you can't solve the system of equations because there are too many V's that fit this equation, system of equations. Okay, so there is this ambiguity here if determinant of A is equal to 0. So that's the importance of determinant. So in this video, we saw determinant and inverse of matrix and system of equations. Thank you for watching.